Sections in OpenMP allow for task parallelism. With sections, a specific portion of code is split for concurrent runtime. First, parallel, using #pragmaOmp parallel, creates the worker threads. When calling #pragmaOmp sections, what essentially occurs is that the team of worker threads has work divided amongst the created threads. Each created thread gets one independent section that each runs a specific task or code snippet. Each section runs a singular time and synchronizes with the other sections at the end. As such, threads that complete early wait for other threads to avoid race conditions. Sections avoid race conditions because the results from each independent section finish before moving on to other snippets due to a barrier at the end of the section snippet. When comparing the C++ OpenMP and Python omp for pi library syntax for these sections, in C++, the compiler parses each pragmaOmp section, creating a new section block. At runtime, each thread is assigned the portion that is in the specific section body. Python does not use pragmas, so instead it records the blocks as independent sections in the runtime with a specific internal index. These threads are assigned an internal index, with each thread calling omp section n, where n is the integer number assigned with the index. If the thread index and n integer match, that specific body code is run. For example, here it says if omp section 0, this would refer to the thread that is corresponding to the internal index 0. The OpenMP C++ library also allows for data sharing between threads. Using first private, a specific thread can get its own copy of a variable, set to the initial value before entering the parallel region of code. The single directive allows for only one thread to run a specific block of code. That thread will run the code inside the single snippet, with the other threads waiting for the single code to complete before doing their work. In OpenMP, copy private copies a computed value from a thread to all of the other concurrent threads. As such, this is nearly exclusively used with single directive threads. For the C++ OpenMP library and the Python omp for pi library, data sharing with private/broadcasted values is slightly different. In the C++ implementation, the variables used first private, copy private, and single require a declared type. As C++ is a statically typed language, meaning its variables are checked at compile time for a type. With Python, variables are dynamically typed and inferred which type at runtime. In terms of scoping, C++ variables follow a block scope, where variables are local to that specific block of code. Since Python doesn't support this, instead Python uses helper functions like omp parallel 1 to simulate block scoped variables in parallel regions. OpenMP can utilize tasks, which are blocks of code that can be executed independently by any thread in the worker thread team and dynamically scheduled using #pragmaOmp task. This means that the OpenMP runtime decides which thread executes the task at runtime rather than assigning the task to a specific thread. In the Fibonacci example, single is used to ensure that only one thread starts a Fibonacci computation. Then the parent thread creates the recursive call and creates two tasks for the individual numbers in the Fibonacci computation for the n-1 case and the n-2 case. These tasks enter a queue where available threads can execute the tasks. The task wait block waits for both tasks to finish before executing the return of I plus j, where I is the return of the Fibonacci sequence for n-1 case, and j is the Fibonacci sequence for the n-2 case. The OpenMP and omp for pi implementations differ slightly in terms of task syntax. With OpenMP, the compiler generates a task object for the encased code block following #pragmaOmp task, translating from pragma to a task queue. As explained earlier, Python doesn't access pragmas, so task generation is done explicitly at runtime due to Python being an interpreted language rather than a compiled language. In omp for pi, each task is wrapped in a helper function and submitted to the runtime task queue using a call of _omp_task_submit. Like in OpenMP, omp for pi schedules these tasks dynamically with available threads.